As I talk through some of this short intro, I'd like to get an idea of who's on this call, what your background is, and what's your interest in agrivoltaics. So, Silly, can we launch the poll? Perfect. So if you can all just respond to this poll, we can start to get an idea of your level of understanding on the subject, background knowledge, where you're at, and think about how you might want to engage with agrivoltaics. Um, and thinking about agrivoltaics in Africa, I think we see this great opportunity to take this land use system and really derive some wonderful benefits, especially in communities where there's great needs for water, food, energy security. Today, we're going to hear from people working on the ground about the benefits they've seen and also the challenges and trade-offs with implementing these systems. Um, but I think there's so much opportunity, and I hope that this webinar today acts as a place where we can really just, cover some of the groundwork, the basic concept, where where agrivoltaics is at in Africa, and maybe think about where it might be going and have some discussion at the end that I hope everyone will contribute to, thinking about what agrivoltaics might look like in your local context, your local community, and what benefits you might derive. So I'm going to leave it there and pass it off to the team at South South North. Looking at question one here, I can see that most people are somewhat familiar with the topic of agrivoltaics, but there's definitely people in the room who have maybe never heard about it or have a shallow understanding. So hopefully, we'll have a brief introduction here and that will fill in some of that missing gaps. And as we go into some of these other topics, we'll really build upon that. So, Roy, I think I'm going to pass it off to you.
Thanks, Kai. And welcome everyone. I just wanted to give you a warm welcome on behalf of the African Climate Action Partnership. Give you a quick overview of who we are for those of you who do not know us. But the African Climate Action Partnership is a regional membership-driven network that works across Africa on issues around accelerating and supporting implementation of ambitious climate action for Africa. We believe strongly in the idea of uh, expertise within the continent and looking at how we can leverage existing knowledge as well as peer sharing opportunities to support action across the continent. To do this, we have more targeted sectoral approaches in terms of the work we do through what we call communities of practice. And currently we have 4 communities of practice which focus on energy on one hand, specifically on mini grids, where we look at how we can create an enabling environment to support the deployment of mini grid systems. And then we look in the agriculture space as well, looking at how to support the inclusion of key players within the agriculture sector into the climate policy space and the climate dialogues. And specifically, we have 3 communities of practice in the agriculture space, one on livestock, one on rice, and one on soil. So this webinar is a really great opportunity to explore some of the cross linkages and synergies between the energy and agriculture spaces of work that we do, and we are hoping that we can identify some great opportunities to further this engagement across these two areas of our work. So once again, thank you so much for joining us today. We look forward to the outcomes of this, and are really keen to see where this webinar goes and what sort of opportunities emerge. So with that being said, I'll hand back over to Kai to formally kick off with the content for the webinar.
Wonderful. Thank you, Roy. All right. So I want to start things off by really giving a broad overview of what agrivoltaics is. And keep in mind, this overview is going to have a US centricity to it, to the way we think about agrivoltaics here. And so I want you to really take a look at all of this information and try and translate it to your local context. Think about what might be relevant, what might not be relevant, and share those things, hopefully at the discussion we have at the end. So next slide, please. So when we define agrivoltaics, this definition varies from region to region, country to country, and even continentally. In the US, we really think about this broad definition of agrivoltaics that can include grazing beneath solar panels, crop production, habitat for pollinators or other wildlife, and even greenhouses. And it's the most questionable one might be if you have solar panels above indoor agriculture. That one's really on the fence. Next slide, please. Overall, though, it's this mutual vision of solar and agriculture sharing sunlight between panels and crops. And there's a lot of flexibility in what this looks like on the ground. But we want to have more use from the land than just agriculture, just solar panels. And depending on your context, if you're in a land limited space, sharing between solar and agriculture can really make better use of that land. There's also a slew of potential other benefits. Now, yeah, you can go to the next slide. Thank you. As we think about what agrivoltaic systems look like, we have two broad groups that we think about. And on the top here, you can see traditional utility scale configurations. So these are really energy-centric systems. You're going to have panels that are very close together, and the whole system is going to be built to maximize energy production, with agriculture as really a second thought. So on the left side, you can see crop production where you're generally going to grow crops between these rows of panels. For animal husbandry or grazing in that middle one, sheep and chickens, really docile animals, are quite adaptable to these types of traditional photovoltaic systems, but larger animals can pose a challenge. Ecosystem services on the right side there, when you're planting native vegetation beneath panels, this also works really well with traditional photovoltaic systems. Now, a lot of agriculture is not going to be adaptable to those tightly spaced arrays. And so if you look at the bottom left, we start imagining these alternative configurations, more agrivoltaic and agriculturally centric configurations where you're raising panels, spacing the panels out, spacing the rows out, potentially using systems like vertical mount to allow machinery, to allow people beneath the panels, to allow animals, larger animals, or potentially going down the route of something like a solar greenhouse. Next slide, please. Now, there are trade-offs when you slide along this scale to agriculturally focused or energy focused system. And as I mentioned, as you raise that panel height, that benefits agriculture, but it can increase costs. As you increase row spacing, you're going to lose energy production per hectare of land. However, you might be able to accommodate agriculture in a better way. And same for that panel spacing. Next slide, please. Now, When we think about what agrivoltaics is, and specifically crop production, a lot of different activities you can do, different system designs. And what we've seen is you're generally going to be growing crops between rows of solar panels, but also directly beneath them potentially. Uh, we see a lot of hand harvested or small machine harvested crops. However, depending on system design, you could introduce larger machinery. And your crop performance and yield really is going to vary based on your location, your system configuration, and what type of agriculture you're practicing there. Um, the design configurations are much of what I just mentioned. There might be changes in operation and maintenance needs, and access to water is always a big one. Now, in the African context, you can think about maybe having energy from the photovoltaic system, maybe in a rural place, where there was not electricity already, can allow you to pump irrigation water from the ground, for instance, and create that water source. Next slide, please. Thinking about pollinator-friendly solar, this again, we have a lot of these large utility scale PV systems in the United States, and adapting them to pollinator-friendly vegetation is a relatively straightforward practice and can really benefit, essentially everyone. You can reduce your stormwater runoff, flooding. You make habitat for pollinators, potentially other wildlife, depending on what your goals are, increase biodiversity, um, and even control things like the heat island effect. And in terms of cost and design factors, as I said, this is very adaptable to high density utility scale PV, and you don't need to make so many changes, but it can change how you do operations and maintenance, for instance. Next slide, please. Solar integrated grazing. Uh, Again, sheep have been a real success story. They are very adaptable to photovoltaic systems. They can, mow the vegetation for you, which has reduced O&M costs for solar operators and owners. And it benefits the grazers. The sheep do like the shade, and take advantage of all the forage growing there. When you start thinking about larger animals, though, there are considerations with the animals interacting with the PV array, um, where you have wiring, you have panels, and you have the racking. And so you really have to be thoughtful about how these animals are going to interact with that PV and how you can keep the animals safe and how you can keep the PV system safe. You also have to consider things like fencing around the site, water access for the animals, and give consideration to these two different poles on the system. Next slide, please. When we think about solar greenhouses, these are generally operationally more expensive systems. A greenhouse tends to be a more costly operation than traditional open field agriculture, but there's also opportunity there. And in terms of agrivoltaics, greenhouses generally are intensive. So you have a direct on-site use of that energy, and it can be really beneficial to introduce photovoltaics. There's a lot of different ways you can introduce photovoltaics with rolling PV. You have on the left here, that pink area on the roof is likely some sort of thin film organic PV, which can be even tuned to allow light through that plants can use while absorbing light that they can't use to produce energy. And again, you could potentially call indoor agriculture with PV above it agrivoltaic, but it somehow fits in that realm. Next slide, please. What we really want you to take away from all these configuration concepts is that there's this broad range of what you can do within that agrivoltaic space, whether it is a solar energy focused system or a real agriculturally farmer focused system. As you move towards that agriculturally focused system, you're going to see, more unique designs. And as you increase things like the height and the spacing, it can become more costly to produce the same amount or to produce energy on the same amount of land. Um, in any of these cases, there's important site preparation and installation considerations. You want to really avoid compacting the soil. You want to protect existing vegetation and pasture as possible, because when you develop these PV systems, you want to maintain that land, whether it's for agriculture or just for native vegetation to grow. Um, and there are so many, novel and unique configurations that we can make here. Next slide, please. Think I'm coming up on time, so I'm gonna go through these a little more quickly. But agrivoltaics is really a global phenomenon. You can see there's mapping projects popping up around the world. In the center there, this is our NREL map. And it does include, this whole broader range of agrivoltaic systems, but you can see that there is a lot of activity happening throughout the US. We have this map of India with sites throughout India showing up. And of course, in Europe, you have agrivoltaic systems all throughout Europe of different types, really unique configurations. Next slide, please. Also, where you can find our Inspire map of the US, you can find our data portal, which is a comprehensive, or maybe the most comprehensive repository of agrivoltaic research that you can filter, search by categories and locality. Um, Next slide. And when we take a look at where all that research is coming from, you can see there's hot spots here and there, but you can see that Africa really, as of 2023, which is where that database is currently dated to, there is a lack of research in Africa on agrivoltaics, and this reflects just a lack of agrivoltaic development on the ground. There are not that many systems, but there are some really interesting studies that have already taken place. You can see this example from South Africa where they were looking at Artemisia and thinking about how the shade might, affect the production of this artemisian compound, which has medicinal properties. And they found more of this compound in the shade. So just a quick example. Next slide, please. I'd also like to just point you to this resource, the 5 Cs of agrivoltaic success. This is a report that we've published that breaks down agrivoltaics into these five categories that contribute to making successful projects. Climate, your configuration of your system, the crops and cultivation methods, compatibility between solar and farmer, and then of course collaboration. And collaboration is this one that's crucial. Next slide, please. You really need all of your stakeholders to be on board, and the stronger your team is of broader stakeholders on an agrivoltaic project, the more likely it is to be success. And that can include researchers, farmers, solar developers, and of course, the local community has to be involved. Um, so Alexis Piscaris and our team has done a lot of this social science work assessing, potential benefits and perspectives. So for farmers, we hear that there's, uh, potential for enhanced farm viability, both economic and resilience to climate change, diversification of revenue, better land use, and water and energy savings. For the community, you can think about economic and workforce development, reduced pressure on farmland, protecting cultural heritage and points of local interest, and of course, local food, energy, and water resilience or security. And from the industry side, we actually can see improved community acceptance where, communities might be opposed to PV. Agrivoltaics might be a more appealing solution. There's potential savings on operations and maintenance, increased access to land because of that perception of agrivoltaics being more appealing maybe than just photovoltaics. And of course, all those system co-benefits. And again, this is very US focused. The benefits that we might envision for communities throughout Africa might be different. And I think there's a great opportunity to explore that. Next slide, please. At the same time, agrivoltaic systems are not a magic bullet. They have trade-offs and takeaways, and every system needs to be considered uh, uniquely for what it can bring and what challenges it can bring. So farmers have concerns about impacts on soil, of course, crop productivity and yield, access to land, and the preservation of farmland. Challenges with the infrastructure, how to navigate infrastructure and operate within a PV array, and long-term planning, the decommissioning of that array, or what the future will look like 40 years from now on that land. Community concerns about cultural heritage and landscapes, the land type and aesthetic. You are introducing a PV array to the land. How does that change its aesthetic value and the land use? And of course, distributional justice. So there are all these potential benefits, but who is seeing those benefits? How are they being distributed, and is it equitable? Industry concerns, of course, the liability of newness. Agrivoltaics is still relatively new, and there's uncertainties around that. And, industry does not like uncertainty. Again, cost benefit analysis, uncertainties. What are those trade-offs with the costs? And how do they play out? As some of these benefits can be harder to quantify or put numbers to. And political feasibility. Um, so next slide. I hope that really lays some base groundwork for the concept of agrivoltaics. And I hope you think about these systems in your local context. And I'm going to let our other wonderful speakers give you some more concrete examples and show you what's happening on the ground. So you can always reach out to Brittany Stay or myself. We were with NREL. Thanks for attending. I guess I might have a couple minutes for questions if anyone has questions. I might be over time though, so we can save that for the discussion since this is really a broad overview, and I can answer questions in the chat. How about that? Do we have Greg here, our next speaker?
Kai, there is a question.
Yes.
Yeah.
From
do you want to maybe ask your question while we get Greg to start getting his presentation ready?
Perfect. Ayula, do you want to go ahead? Can the audience unmute?
Good afternoon, everyone. It's afternoon here. Please, can you hear me?
Yes.
Yeah, thank you very much for the work you are doing. And agrivoltaic is something I'm really interested in. But I just want to ask this quick question. I have a plot of land, and I'm looking at maximizing it for agrivoltaic. How can I go about it? How can I go about it? And one thing I'm equally looking at, because it's a new area, I'm looking at using it to power some homes around that area. Is it something that is feasible that I can do? Thank you very much. I hope you understand my question.
Yeah, no, thank you so much. That's a great question. And I love to hear that. Um, there's, there's a number of steps to starting a project. One of the big questions is going to be, is there already any electrical infrastructure there? Is there a grid that you're going to tie into? Um, if not, how are you going to connect your solar panels to the homes in your community that you want to connect to? Do you want something like, some type of battery storage so that, yeah, you might have energy into the evening or early morning? Um, and yeah, I think it also depends on your level of expertise. Is this a system that you want to design and build yourself, or is there someone in your community or nearby that might have the capability to build a PV system? Are there potential partners in your community that are interested in developing photovoltaic systems? If you can connect, with an organization or someone who wants to build PV, then that can be a great starting place, and start having those conversations, talking about your needs and how they might align with a developer's needs, for instance, or whoever might be building the system. Um, yeah, conversations, talking to the right people is really the start of these projects. I hope that helps. How are we doing with getting Greg on board? I think we could also always bump Brendan up if he's ready to go.
Yeah, we can't find Greg, but we can go ahead with Brendan if you're ready to go. Or Greg, if you are in the call, can you unmute yourself and let us know?
Otherwise, we can get going.
Yeah. Okay, we can get going with Brendan's presentation.
Perfect. I'll reach out to Greg and see if I can locate him. Thank you all.
Brendan, over to you whenever you're ready to speak.
Yes, I am. Thank you very much. I notice I can't turn on my camera, but that's not a problem. Good afternoon, good morning, everyone. My name is Brendan Bingwa. I'm from the Fraunhofer Institute for Solar Energy Systems, ESA. And yeah, thanks to Kai for giving a good introduction, an overview about agrivoltaics and some of the benefits. Greg sort of tied in perfectly because I'm going to take it in a different direction and talk more about the business models that we're trying to implement, and finance models as well, to try and upscale and make agrivoltaics as sustainable. And we're doing this through two projects we're actually working on. I'll focus on one of them today. Next slide, please. So just a quick recap, because it's always good to contextualize this, but we know that there are multiple benefits for agrivoltaics. This sketch comes from a project that we have in Mali, Gambia, called APV Maga. I'll talk more about the project later. But what was important for me to show here was the benefit, or the potential benefit, of agrivoltaics along the agricultural value chain. So the contribution to energy, that's direct use of the energy produced, for providing services such as cold rooms and food processing, so use of the actual energy, and also from the agricultural component. So as Kai mentioned, the potential benefit of shading on the microclimate, so improvements in the microclimate, hopefully, especially in the harsh climatic conditions that we find in many parts of Africa. And subsequently, the potential to improve the crop yield through those microclimatic improvements. Yeah, sometimes this is not the case if a crop is too shade tolerant, but that's not my focus today on those benefits and negative impacts. And then from the water aspect, as you can see here, this is actually what we will be implementing in the project, which is a V-shaped for rainwater harvesting. It doesn't have to be V-shaped to harvest rainwater, but it's just an approach we wanted to try and test in our research. Next slide, please. So just a quick overview before I get into some of the challenges and the barriers to agrivoltaics. So the project Agrivoltaics for Mali and Gambia, Sustainable Energy Production by Integrated Food, Energy and Water Systems, or APV MAGA, for the American crowd out there, not related to any other MAGA you may know of. But yeah, the plan is to build 4 demonstrators, one in Mali of 150 kilowatt peak at the campus of the Rural Polytechnic Institute of Training and Applied Research, IFR, and 3 systems in Gambia, one at the University of the Gambia, one at Fast Community Garden, and one at a private farm. And you know, as you can see from the graphic that I showed before, it's an interdisciplinary project. You know, we want to address each component of the water, energy, food nexus, and also the economic performance of the system. So this is how we want to research. I briefly mentioned our research focus from that perspective. But quite importantly, and what I usually find is overlooked, is the financing and the business model. So, you know, how do we get these systems implemented from either a research perspective or in the long term when we actually want to upscale and have farmers with a small scale or medium scale to actually get these systems built? Keep in mind, this is a research project, so it may not be the perfect solution. It's something we want to investigate through our research. Next slide, please. So Kai again mentioned some of the barriers and challenges that are noticed in agrivoltaic systems. So yeah, related mainly to this economic side of things is the high initial capital costs. So costs in agrivoltaics are highly individual and they vary depending on factors such as the installed capacity, agricultural activity, so the type of crops you're planting, the machinery used, etc., system location, PV module technology used, mounting structure, etc. And the CapEx costs are generally higher than those of conventional ground-mounted systems. Also, there's sometimes a lack of technical expertise in some of the projects we worked in. It's easy to get well, not easy, but it's possible to get the system built in a remote region, but getting maintenance after is challenging. For sake of time, I'm not going to go through the remaining in detail, but you can see that, you know, land tenure and legal frameworks can be barriers. Energy infrastructure and grid access, social and cultural acceptance is a big one. Policy and institutional support as well, or the lack thereof, I should say. Next slide, please. Oh, okay, they're ready. Development aid projects. So now it was interesting this was, I guess, a bit of inspiration in this MAGA project. So you'll hear me referring to it as the MAGA project. In that we know that these development aid projects, which we have seen, so we looked at it from 2 aspects in terms of research and development projects, and also just in the long term. And it was important for us to look at it this way because, you know, eventually our infrastructure that we're building in this project will be left on site. And what we've seen before is, you know, the white elephant, of course, public funds, which we receive for our projects. Everyone's cheering and happy to have a nice idea implemented, brilliant idea with many potential benefits such as agrivoltaics. So start off the project, everyone's motivated. And then at the end of the project, you see the pictures on the right, which are from Gambia. So lack of maintenance of equipment, drip irrigation systems pulled out, etc. Next slide, please. This is a complex financing model. And as I said before, it's maybe not the perfect solution, but it's something that we wanted to explore as project partners in this APV MAGA project. So how do we get the systems built when there's lack of, or these challenges and barriers to financing? So we looked at ways that we could then, excuse me, find financial models to provide decentralized renewable energy through partnerships of public, private, and private sectors and donors. And in Mali, in the case in Mali, for example, it required an SPV to be formed because IPR is a public institute, and in the case of the other SPV member is a NGO, an NGO. So the light green colored boxes are the German partners who have contributed to funding for the infrastructure. I forgot to add there that UNU, United Nations University, also did provide funding. So Fraunhofer and UNU provided, and then each have components in terms of whether research or contributing to some kind of mechanism of getting the system built. The hope is that the SPV that's formed between the local partners can then operate the businesses that are attached to the agrivoltaic system. So in the case that I mentioned before, maybe a cold room or processing plant, so a cold room will be installed at the system in Mali. IPR, ideally what would be a good case is the SPV actually owning the system and then getting a power purchase agreement with the use of the electricity. In this case, it doesn't exactly work, many complicated reasons. That's why the project is delayed. But IPR gets some benefits of the system being that it's installed on its site. They get the electricity, they contribute to agricultural research, and just also involved in other research aspects. They conduct the actual agricultural experiments as well. Next slide, please. On the business model, we did definitely not try and reinvent the wheel. What I mean by that is we looked at business models that were existing and we tried to bundle them so we could get the maximum benefit from the agrivoltaic system. Really try and maximize along the agricultural value chain and also the synergy between agriculture and energy. So, the things we are applying in the project, I'll take the case of the FAST community garden, is energy as a service. So the agrivoltaic system is connected to a cold room where the farmers or the owner of the system can actually, and the farmers, which is the community garden, can actually store their own crops and then also rent space out to the other farming communities or the small farmers that are around. There's also a peanut press, so a groundnut press on the site that's connected, and they'll produce groundnut oil, peanut oil for sale. We can't implement direct energy services for many reasons, technical, etc. Legislative, not in place, but it would be nice as well if you could connect homes to the system. Very technically challenging if you can imagine the cabling issues, but it offers things, technologies such as pay-as-you-go enable the potential to have energy that is metered in a sense. Of course, you can have the water services, so pay-as-you-go water, or not pay-as-you-go water, but getting a chip card which allows you to get drinking water from water pumped either from a well or water that's collected in a storage container, or providing water through drip irrigation. And of course, the simplest case is just the sale of the crops from the agrivoltaic system. Next slide, please. I think I'm out of time, so I'm wrapping it up. In terms of sustainability, what does this mean? So, I put some keywords here, but there could be many, many others. It's needless to say that when you create a good sustainable business model that ensures that people are invested in it, that benefits the community, that creates jobs, that brings purpose and drive and meaningful work, sense of ownership, accountability, etc., there's the tendency or the likelihood that the project could be continued. And that's our goal through our project. As I say, it's not maybe not the perfect solution. Research we'll find out with time, but it's one of the reasons why we use the research platform to apply such financing and business models and hopefully get some results that can help us to learn and then optimize these business models. And thank you very much. Next slide. Yep, thank you very much for your attention. My contact details are below. There's so much more I could talk about both projects in Mali, Gambia, and Namibia, but hopefully that gave you an overview of what we're trying to do. Thank you again. I think I have time for some questions now, because I won't be able to attend the session later.
Exactly. Thank you so much, Brendan, for this presentation. Yeah, if anyone had any questions before Brendan needs to drop off, please just raise your hand so that we can get to those. Please, if possible, raise your hand and unmute yourself so that we don't miss any questions in the chat after Brendan leaves. But Paul, please go ahead. Paul, you're free to unmute yourself and go ahead.
Okay, unmute. Yeah, sorry, I couldn't unmute myself. Thank you. Thank you, Brendan, and thank you for everyone who has been presenting. This is very interesting. Yes, I was asking Brendan for the economic model. Have you been looking, for example, the cost, for example, if you are dealing with small farm, the cost of installing that PV compared to the outcome, and eventually where those solar panel came from, and also all the structure of the solar panel, will it be more beneficial to develop them locally or just to bring everything from outside?
That's one of the complexities of all the projects we're currently running, is that yes, we have an economic model which considers the material costs. So depends on where your supply is, if it's not locally. But as we know, things like PV modules and inverters, you can't really beat the prices of the larger manufacturers. Where there is a significant amount of potential saving is if you can harness the local manufacturing capacity for that substructure, so the metal use, because that's where a lot of the cost is from, especially in these high elevated systems. So actually in the project in Namibia, we're trying to use local manufacturers, local materials and components, and that should bring some cost savings. Unfortunately, like I say, we've run some simulations on the model with different scenarios, and yeah, you can see that if you have all these factors playing in, if you can bring that cost down, the payback period or the return on investment is a bit longer, but it could be a viable business model. And that's important to us to now test it and see within this constellation of not only the business model side, but can people run it effectively? But yeah, that's another topic. But yeah, to answer your question, yes, we've run some models, and it just depends on where your material is. And if you can get it locally, you do see some great cost savings.
Sure. Okay. Thank you.
You're welcome.
Thanks for that question, Paul. Are there any other questions for Brendan before we move on?
Just to say quickly, I can stay till 4 p.m., which is another 15 minutes or so. So if you have any questions in the chat, I'll be able to try and respond to them before then.
Perfect. Thank you so much, Brendan. And thanks for your time today.
Thank
for that
you.
great presentation.
Thank you so much.
Greg has joined us, so I'm going to hand over to Greg. Greg, will you be sharing screen from your side?
It's not the
Greg, we can see you, but you seem to be muted. Just give us a second.
Okay, thank you for that. Sorry, I could not unmute myself. I'm sorry for the trouble this morning. We had a little medical situation here, and so if you hear the helicopter, it's because I'm outside of the hospital. Thank you for the opportunity, and thank you for the organizers who are bridging our hemispheres and our continents to do this important work. We're really excited to be able to participate even a little bit across our team to share a little bit about what we've been doing. And so I was going to share a few slides based on some of our projects. And more specifically with this set of slides, describing how agrivoltaics can be a community-based solution for food, energy, and water resilience. My name is Greg Barron Gafford. I'm a professor in the School of Geography, Development, and the Environment at the University of Arizona, but also represent a few other organizations, including a research station called Biosphere 2, north of Tucson, Arizona, and the School Garden Workshop, which is a community-based organization on education, experiential learning around food for school-age children. And even though I'm the one presenting, like many of the other presenters today, I represent a lot of individuals who have helped make this work possible. So I think as we've been talking about today, and many times we do with agrivoltaics, we have challenges associated with food, energy, and water. And working as an ecologist in this renewable energy space, been recognizing that more and more part of the challenges that we create by trying to solve some of our problems is that we're working in silos. And so if we see a zero hunger problem, we go to the food for or the energy for water program and think about ways to bring solar-based irrigation, for example, without thinking more holistically. And with our project, what I've been especially excited about is how we've really tried to move beyond focusing on those 3 sustainable development goals. And we've really started with the last one, which frankly, I was surprised that we were often skipping past, which is working on partnerships for the goals. So this particular project is a mash of multiple countries working with multiple communities to identify the public group that we were working with. We actually met with about 12 different communities around Kenya, trying to find the right capacity to think holistically in terms of were they looking for just an energy solution or just a water solution. And then because we had seen examples of communities developing a technology like solar, but not having the capacity or even the interest in doing the maintenance work, we were trying to find community that had examples of being able to do some of that technical infrastructure work as well. The other part of this is that acknowledging that our particular effort might seem relatively small scale. And as we've talked more about agrivoltaics, and we've done our own relatively small scale site, which is about 20 meters by 20 meters, is what does it mean to scale agrivoltaics? Particularly in the United States where people want bigger things more often, they are not thinking about scaling agrivoltaics, meaning replicating a model that's working in multiple places, but rather going really large installations. And so we've been really questioning what are the best ways to bring multiple impacts to the local individuals and retaining the impacts of that installation more locally. So this work in Kenya is actually part of a bigger global collaboration that we started initially with our project in the University of Arizona, but reaches into Mexico, Morocco, so on the Western African side, Southern Israel, and the project talking about today is a different one than Richard may have mentioned about Kenya. And so this particular installation, what we were looking at was the community needed to bring water to this reservoir. And so we're originally going to just be introducing renewable energy through solar. But when we talked about the potential for agrivoltaics and the reduced evaporation you see in the soils underneath the solar installation, when you see the differences in being able to work in the shade for longer periods of time, when you see the benefits in terms of food production, we convinced them to consider trialing an agrivoltaics installation. And it looks like my picture is going to cover my others. But then we took the time to meet with the community members and to hear about some of the crops that they were growing. What were the challenges that they were having in terms of nutrition? What crops did they want to grow? And we heard a lot about things that used to be able to grow, but now it was too hot or it was too dry. And yes, it does look like my other slides are being covered. But in this last instance, then meeting with community members slightly outside of our project area to hear what were some of the challenges for the food production that you can see peeking through. And it was primarily water-based in this portion of Kenya. And so the other way we were using our network of sites is before that particular project could be built, and because Arizona represents the climate future of this particular community, we brought back some of their crops so that we could study them in our agrivoltaic installation and give us insights into what's possible. So we brought back some of the Kenyan kale, cowpeas, zucchini and squash, and Kenyan spinach, which in the US we call Swiss chard. And here are just a few pieces of data. What we're looking at here are the yield differences in grams per plant so that we could think about ways of upscaling and what it would mean. And all of these graphs, the green is the agrivoltaics, because quite frankly, that's what the plant stayed, as opposed to brown, which is in the full sun treatment, where we did not have the agrivoltaics installation or our control treatment. And when it's just amazing to see how much agrivoltaics could increase the yield of these plants. And so instead of having this food versus energy conflict, we were seeing sustained food production because of the energy overhead. And so you can see 3,000% increase in yield of spinach. It makes the 200% increase that we captured in terms of cowpeas and zucchinis seem unimportant, but still 200% is significant, especially when you think about the orders of magnitude more people receiving that healthy food. Then because agrivoltaics is meant here to lessen the impacts of drought, and because the solar overhead was being used for pumping, and we thought, what if there ever is a limitation to the ability to pump that water, or more people tap into that water use in terms of the families nearby? We also ran that experiment with half irrigation, and you can see mixed results. The spinach overall declined, but we still saw this significant yield in spinach production because of agrivoltaics under the half irrigation. Cowpeas with half irrigation in the full sun were basically all dead, but we actually saw increased yield. And that's partially because of the nature of this plant being in a dryland environment, and zucchini didn't seem to care. Now, because time has passed, we have been able to install this project, and this one is actually happening now, has been for about 7 months in Makwini County in Kenya, which is on the eastern side of Kenya. Here you can see pictures of some of the moms, because that's who these women represented in the community, the moms of the children, planting, growing, and already having their third cycle of crop production. And I've been showing this particular image of cabbage because the moms in our initial interview, some of those pictures you saw earlier, mentioned that cabbage was a sustaining vegetable that they used to grow quite a bit. But this is one where it's simply become too hot to produce. And the pictures don't lie. You can see the cabbage production here. But in addition to producing this food, because we are located on a school campus, it was part of the reason we showed up on the school campus to do this project with the community was that the food could go to the children. The other part is so that we didn't get into conflicts over ownership in terms of who was directly benefiting from the energy production. It became and stayed a shared resource within the community so that irrigation pumping could benefit all of the farms in the perimeter. But because of that original interest in experiential learning around food and food sovereignty, the kids were able to help with this work and then have that additional co-benefit of having water. So that was my set of slides, and I'll stop sharing there so that we can get back to the conversation.
Thank you so much, Greg, and thank you for making time despite having a tricky morning. Are there any immediate questions, or do we want to hold off? And well, maybe let me pose this to you, Greg. Do you need to to jump off, or do you want to take questions now or stay on till the end?
I'm good, thank you. I can stay.
Okay.
I have a question.
Please go ahead.
Wait, let me see if I can have my camera on. No. Oh, yes, my camera is working. Hello, Greg. This is Angela from Germany. I remember one interesting point that you said at the conference in Denver, that you said the women choose a special crop because they would get more money than just the best crop for the nutrition. Could you elaborate on that a little bit? I think it's a really interesting point.
Yes. And hey, Angela, so good to see you.
Yeah, good to see you, Greg.
Global conferences bringing new people together.
Uh-huh.
And so in the first two sets of crop production, we really were stressing, gosh, the sun is so intense. We really were stressing food production and nutritional access. But as the women, the moms in the community, were recognizing that they had the ability to negotiate a little bit more with the middlemen, the interest in about half of the women has changed. And they, as Angela was pointing out, they have been asking about switching from nutrition filled crops to crops that are of higher value. And so they were asking about the potential of producing strawberries or some other crops that are not typically grown in the area that they could sell. And part of that is because if you could see the pictures of the women behind that one map, most of the community members we were meeting with were women because so many of the men under 30 had moved to Nairobi or the other cities. And this would be their way of finding enough resources to go visit family. And so it's turned into an interesting social question of, we originally came to it, the project, thinking about nutrition, and now they were trying to balance nutrition and the other sustainable development goal of just boosting overall well-being, in this case, being able to reunite with family members.
Thank you, Greg, for your presentation. It's very interesting to see. I cannot raise my hands for some reason, so I'll just go ahead and ask my question. You looked at yield parameters. Do you also look at quality parameters for the crop, their nutrition value?
Yeah, great question, Nora. Thank you for that. We wanted to. Part of our challenge has been finding a lab where we could process these samples. So for the first 3 cycles of crops, we have not. We did find a lab in Nairobi, but they wanted a lot more material. And not only does that mean taking away food, but it's quite expensive. So the postdoc in our group has developed a pathway for bringing some of these samples in. And this is definitely one of the highlighted kind of research questions of another graduate student. So I'd be glad to connect you to so y'all could talk more about this.
Well, I can recommend one institute is the Leibniz Institute for, I think, vegetable production. The professor is Nicole Van Dam, who is specialized in secondary metabolites. She is the director of the institute. I can't put her name. She was my thesis supervisor a long time ago.
Oh, perfect.
And I did my PhD in chemical ecology. That's why. Okay.
In which country? Germany.
I work at the Max Planck Institute, but now I work for BayWa and also Agrivoltaics.
Nice.
Thank you.
Yes, with this particular project being in Kenya, the challenge was getting the samples out of Kenya. Thank you.
Tokyo-san, do you want to go ahead and unmute yourself and ask your question?
Thank you very much, all presenters. Thank you, Greg. My question is not really a question. I wanted to say perhaps there could be something like the cost that is associated with installing the system, let's say per given area, so that farmers can know that, okay, if I've got a high value crop, like we're talking about strawberries and all that, somebody should know that, okay, within 2 years, I would have recovered all my investment or within a certain specified time. That's all that I wanted to say. Thank you very much.
Yes, thank you. And I will just point out that I think I completely agree. And one of our challenges with being able to do the numerical modeling on how expensive the upfront cost is, and this is a question that Richard, who spoke already, and I have talked extensively about, is every time there's a new agrivoltaic installation in a country, it seems to be way more expensive than the second one. And that's because there is so little consistency in terms of across country installations or the people who are in charge of those installations. And so I don't think we have a really good handle on how much the second or third or even fourth installation of agrivoltaics is in each of these countries because it's still so new. But you're absolutely right. That is the kind of number that we need so that we can give out this information and share it. Thank you.
Thank you so much, everyone, for the questions, and Greg, for your great presentation. There's definitely an opportunity at the end of this session as well to continue this discussion. But for now, we're going to shift over to our next speaker, who is Richard. Richard, please go ahead.
Hi, everybody. Can you hear me okay?
Perfectly, yeah.
Excellent. Can I share my screen, or do you want to share my slides?
Prefer to share yourself. You're welcome to
Okay,
take
yeah,
over.
I'll just do that quickly. Oh, it's taking me to, oh no, here we go, share. There we go. Right. Have you got this okay?
Yes, you're not presenting my jet, but we can see your screen.
Excellent. So good morning, good afternoon, everybody. Thanks very much for putting on this this very important webinar. It's also great to hear Greg's updates from his research as well. And I just want to first say that I really liked one of my favorite things from his presentation was his real life demonstration of how the partial shading can be beneficial to a plant, but in this case, a person. So Greg was sat there in the sun and he was a little bit stressed, maybe uncomfortable from the sun. And so he moved into the partial shade. And this is exactly what we see with the plants in these hot locations. And in fact, I do also know that as well as looking at the impacts of the partial shading of the sun on the plants, I also know that Greg and his PhD student Tally are also looking at the impacts on the people working in the fields as well. So this does just extend, it extends beyond the crop side and the energy side, but also the impacts on people. So I just wanted to mention that I appreciated Greg's feeling stressed in the sun. So moving on to my presentation, I'm now a research scientist at SINTEF in Norway, but previously I was working at the University of Sheffield on the Harvesting the Sun Twice project, which is what I'm going to present today. And this was a project that aimed to look at the livelihood benefits of agrivoltaics in East Africa. And to do that, we had two pilot systems of agrivoltaics, one in Kenya and one in Tanzania. And in this presentation, I'm going to show the main performance results in terms of the crops, the energy, and the water conservation from the sites, and then some of what that can mean for the local stakeholders. So we had two systems. The one in Kenya was a grid tie system supplementing an existing electricity supply to an agribusiness. The other one in Tanzania was an off-grid system. So it's providing new electricity to a farmer training center. And so that system has batteries as well. We had a 50% panel density, which in European terms is considered quite dense. But with the some of the main stresses on agriculture in East Africa being water availability, water loss, and heat stress, we went for a more denser system. So I've only got 10 minutes. I'm going to jump straight into some of the basically the methods and the results. You can see here the two systems that we had. One of the things I want to point out is that we have the rainwater harvesting. So we have these very nice, flat, slightly angled surfaces from the solar panels. So when there's a heavy rainfall, we can collect the rainwater that's running off the panels, and then we can store it in storage tanks to use later on. So that's one of the things that we've found very quickly, that this isn't just about food and energy, but it's also about water, as we've heard previously from Kai, Brendan, and Greg as well. Just a few photos here. It's a bit of a pity that I actually removed the photo we have of cabbages growing underneath the system, because it'd be lovely to have that comparison with Greg's cabbages as well. But we can see with these photos that you have these nice, healthy looking plants that are growing underneath the solar panels. You can see some water that's being collected from the rainwater harvesting system, and there's some photos of the construction as well. One of the questions earlier was about how do we go about developing an agrivoltaic system. What we did was reach out to a local solar developer in East Africa. In this case, it was Chloride Exide, and they develop rooftop solar, ground-mounted solar. They're solar developers, and so we said, hey, can you do something a little bit different? And we want to raise this system up, design it in a different way. But that was our starting point, was to speak with somebody already in the area locally who installs solar. They install grid tie, they install off-grid as well. So that was our starting point. So now I'm jumping into the results. Of course, we were providing electricity, and in the case for the grid tie system, that meant that the agribusiness was then saving money on the energy bills. And you can see here the electricity consumption from when the project started at the start of 2020 up until when the system was commissioned. And then you can see those yellow bars are much smaller since we started producing electricity from the agrivoltaics. The numbers at the top, that's showing they saved about just under this is in US dollars as a comparison. They were saving just under $6,000 a year. But when we model what the system could produce if all of the electricity was used, it would be about $18,000. So it's slightly lower in this case because they weren't using all of the electricity produced. If they had battery storage, then that could capitalize more on the electricity that's generated. Although, of course, batteries are very expensive. One of the main take homes here, and I think Greg's slide is his few thousand percentages put some of these to shame, but we're seeing that the crop yields vary depending on the crop type. Some crops are more shade tolerant than others, and those crops will perform better or may perform better than some crops that may really need that full sun. What you can see here is that some of the crops had significantly higher yields. Some of them weren't so different between the agrivoltaic plots and the neighboring open field control plots, and some of them were lower. Don't worry too much about reading the plot that's on the right, but on the left, the table's this table summarizes this. But what you can see from the labels on the graph is that all of the crops, actually apart from the beans in general, all of the crops were producing a good amount of income. So even if a crop has a slightly lower yield compared to the control, it's still producing food, it's still producing income for the farmers. And in some cases, actually, it was the crops that didn't perform as well compared to the control were still producing the greatest amount of income per hectare because they were the most valuable crops. So just because it's a slight decrease in yield doesn't necessarily mean that it's a negative result in terms of the practical implications for the farmers. I'll talk a little bit more about the beans though. They had the biggest change, but the reason isn't so much that the beans were necessarily performing especially well, but it's actually that more plants in the control plot died off. They were grown during a period where Sustainable Agriculture Tanzania, the host agribusiness that was hosting the site in Tanzania, they wouldn't normally grow the beans during this warm period, but they wanted to try them. And what they found was a lot of the control plot died off, but not so much of the agrivoltaic system. And so that kind of raises the question, could this reflect how under future warmer climates, agrivoltaics could add some resilience to food systems by reducing the number of plant losses? So that's an interesting potential that we could see with a benefit of agrivoltaics under future conditions. We had a similar finding with the maize as well, though not to the same extent. Some of the morphological results. So again, I've just said the beans and the maize had greater survivability. There's also the market aspect. So what's the marketability when these crops are on sale? at a market stall. Sustainable Agriculture Tanzania is an organic farm and it's an education centre, and then they sell the organic crops at the local market. And they were saying that the larger bean pods grown underneath the agrivoltaic system were more desirable at market. We did find that the maize had slightly smaller cobs, but we were also quite pleased to see that the maize grew very well in itself. It's a staple crop in Tanzania. So it was great to see that the maize could be grown successfully under the partial shading of the panels. Like I said, I removed the cabbage photo, but this photo of the Swiss chard is one of my favorite photos, just showing the extent that this particular crop can grow underneath the panels. And that was one of the plants that had one of the biggest yield increases compared to the control plot. So just to summarize on the crops, we're seeing different results, and it varies depending on the crop type. But one of the things that was kind of almost through and through that we saw with this is that we used less irrigation. So the partial shading meant that there was less water loss, and so we needed to use less of the centralized irrigation system. And we could also provide some irrigation from the rainwater harvesting system as well. And so what does this mean for a farmer? Essentially, it means that they're producing some crops that have greater yields with less water input. So it really is kind of a win-win there, from the food and the water side. And then, of course, they're producing the electricity as well. So when we consider that we're growing food from this land, we're also producing electricity, we have to compare, okay, how's the land use productivity compared to if we just had it as a farm or just had it as a conventional solar park? So using those as baselines, open field system gives you a food value as a baseline of 1 or 100%. And the same if you were to have a conventional solar park. This image here is Garissa Solar Park, approximately 50 megawatt ground mounted solar park in Kenya. And when we compare the yields of the crops, we find that on average with the two sites, there's a slightly greater yield of the agrivoltaic system compared to the open field system, which is a fantastic result. Because the panels are spaced a little bit further apart than they would be in a conventional system, as Kai mentioned, your electricity generation per hectare is slightly lower, but still overall, by combining the two, you have a greater productivity of the land. We've already had a question about the economic aspect, and that's one of the next things that we're looking into, but it's a very important question to ask, is how financially feasible are these systems? Greg's given the same answer that I would give, that it's challenging to get accurate numbers. We know the value of the crops, but when you're producing something new from a research and development perspective, the costs can be higher. So we're now looking to get accurate costs for developing an agrivoltaic system in East Africa, and then we can plug that into our model, hopefully to generate a agrivoltaic levelized cost of energy. So we can then understand and compare different energy systems. So for example, agrivoltaics with conventional ground mounted or rooftop solar over the lifetime of the system. But what I will say from the quote that we had for building this, which is one of the first agrivoltaic sites in the region, was that the mounting structure cost about half of the cost. To raise them up to that height and have the foundations was about half of the cost. And of that, I was given an estimation from the solar developer that it costs about 24% extra to raise the system. But like Greg said, these numbers are based on us developing an R&D project. So if it was being developed by a local business in a more commercial sense, the costs would likely be lower. In fact, they would be lower. So just to summarize the results that we've seen is that the crop yields vary depending on the shade tolerance of the crops, but they're all producing income. So with an agrivoltaic system, regardless of the crop that was produced, we're still generating an income, but some will produce more than others. If it's a grid tie system, then there's a saving on the energy bills. If it's an off-grid system, you're providing new electricity source to communities that previously didn't have that electricity. In our case, SAT in Tanzania, that meant that the farmer training center could then start putting outlets for students to charge their laptops, charge their phones. They could have lighting for evening studying. So it increased the capabilities, the capacity of the training center. I've mentioned the potential for climate change, which is something we need to explore. And also, I really like this more crop per drop in terms of the greater crop yields with less water input. Overall, combined, there's that greater land productivity, but one of the biggest questions is on the economic aspect. And I also really liked the important question about what's the nutrient content as well. And that's one of the questions that actually SAT wanted to know when they were hosting this, is like, okay, we're producing a lot of food, but what's the nutrient content when it's grown under these under the panels? The leaves might be bigger, but how are the plant resources distributed as well? And then a final point here, just a little bit of a nod to one of the next talks, is that we've also done some spatial suitability modeling of where agrivoltaics could have the biggest impacts or the most relevance in East Africa, and Tali is going to present on that shortly. So just quickly, there's also a 7-minute film, so I'm not going to play it now, but there is a QR code up there, and the title on these slides, which I believe will be shared later, is a hyperlink to this video, and this shows some footage from the site in Kenya, and also of the work that we're doing on agrivoltaics in Norway, which I'm not going to talk about now. But I will say it's a bit unfortunate that they filmed it. Sometimes in summer it was 27, 29 degrees, but they decided to film this in February, and there's literally ice on my beard, and it was -15 outside when they were filming. So yeah, there's a bit of a contrast between where I'm working now compared to where I was working a few years ago. So thank you very much, everybody. I hope that's been interesting for you. And if you have any questions, then please let me know. And I'm looking forward to a good discussion around this topic. Thank you.
Thank you so much, Richard. I see we already have a few hands up. So, Poli-san, you want to come in again? Please go ahead.
Thank you very much for a very informative presentation. I just wanted to know how durable are they, this agrivoltaics? Does it take maybe 15 years or 2 years or whatever? How many years after how many years will somebody has to replace them? And the second one is about here in Southern Africa, we normally experience hails. So I'm thinking, I just want to know, are they durable enough? Can they stand firm against such things? And then the third one is about the issue of photosynthetically active radiation. Have you measured it so to say that, okay, maybe when this photosynthetically active radiation is below this amount, then the yields seem to be compromised when it comes to a certain crop? Or did we just put those panels without having measuring a photosynthetically active radiation? Thank you very much.
Yeah, thank you very much for those questions. I'll take the last one first, about the PAR, the photosynthetically active radiation. I didn't show it, but we did measure PAR at both sites. The results were as expected, that the PAR decreases in the partial shade. So we compared it in the open field control. Then we looked at the PAR underneath the gaps between the panels, and then we looked at the PAR directly underneath a panel. Because if you think about as the sun moves across the sky, you'll get this kind of like movement of shade over the crops. So it's not always that some crops will be, well, depending on how you've designed the system, it's not always that some crops will be in shade and some will always be in the sun. So we found, as expected, that the PAR was greatest in the open field control, then underneath the gaps between the panels, and then directly underneath the panels. We haven't compared that to the yields, though. We haven't looked at the relationship between the PAR and the yields. But that's something that, you know, that's an important thing to consider as well, and that will vary for different crops. The other two questions about the durability, lifetime, and also I'll wrap the hail into this as well. So there are some things where you have to think of agrivoltaics in a very agrivoltaic specific way that's very relevant to the farming aspect. And there are some things where you can lean on just conventional solar. So the solar panels we're using are the same solar panels you would put on a rooftop or on a ground mounted system. Of course, they are under additional stresses in some ways. So being raised up, they may be under greater wind loads, perhaps. Also, depending on the farming activities, there may be other stresses or dust buildup, depending on how the system is managed. So there may be greater stresses, but approximately we work on it being comparable to the 15 to 20-year lifespan of a conventional ground-mounted or rooftop solar park. In terms of hail, I know that there's some research that's been conducted in the Netherlands that find the solar panels can withstand hail. They are designed to. They have a glass covering. Perhaps not some of the most extreme cases of hail when you get large tennis ball sized hail. I can't comment on that, but heavy hail, the panels are designed to withstand that with the glass covering. And what they actually found was that the panels were fine, but the raspberries in the open field system were not. And so the soft fruits were damaged by the hail, but the raspberries that were underneath the solar panels, they survived and they were fine. So it's another case where the agrivoltaics provided essentially like a protection for the crops underneath. And actually that was an interesting study, because what they found was that when there wasn't the extreme weather, the open field system produced a slightly higher yield. So one of them had a yield in open field like this, the yield of raspberries was here, slightly greater in open field. But then when there was the hail event, this one went right down. So again, it's kind of buffering some of those extreme threats that can be placed upon farming systems. Okay. I hope that's answered your questions okay. And I'm not sure if we have much time for others or not. I think we still have 2 more talks to go. So.
Oh, thank you. Thank you very much. Short one. The effect of planting date or the season, did you really consider it or something? Have you done such a research?
That's a great question. That's a very, very important question, actually, and that should have been mentioned earlier as well. Yeah, as well as the variability on crop type and also location, also different times of year and different growing seasons will yield different results. The one thing we did test where we grew onions at different times of the year, the results were not that different, but there was some difference. There was a slight difference in one growing season. There was no significant difference between the control and the agrivoltaic plot. And in another growing season, the agrivoltaics plot was lower. So growing season will have an impact. And as I mentioned with the beans, the farmers grew the beans during a period they wouldn't normally grow them. So yeah, growing season is something to consider with which crop to grow as well.
Thank you so much, Richard, for that presentation and for the questions. Yeah, I think in interest of time, we're going to move straight along. And I think we are moving on to Brittany.
Yes. Hello, everyone. Thank you for having me. If you all want to share my slides, happy to get started. But good morning, good afternoon, everyone. I'm for some reason unable to turn on my camera, but that's totally okay. You'll see some pictures of me farming underneath panels. So my name is Brittany Stay. I'm also a researcher at the National Renewable Energy Lab. And as I was saying, I was a previous agrivoltaic farmer in the United States. I worked at a 1 megawatt system, about 5 acres, pictured here, where we did a diverse vegetable production. And Greg also does some research at the site as well. But today I'll be talking not about that, but about the co-benefits and opportunities of integrating regenerative agriculture into agrivoltaic systems. And today we'll call that regenerative agrivoltaics. Next slide, please. So I just wanted to give a little context before I jump in. Of course, as we all know, climate change is caused by increased greenhouse gas concentrations. And although many African countries are some of the least emitting countries globally, parts of Africa will unfortunately be some of the most impacted areas by the effects of climate change. One specific group being immensely impacted is smallholder farmers. In some parts of Africa, farmers will likely see more frequent and more intense extreme heat and drought events, which can lead to reduced soil moisture and health, which can obviously have poor impacts such as decreased food yield, increased food prices, and reduced food security. Other things like quality of life, labor capacity, household income, and nutrition can also be negatively impacted. So one potential solution for lowering greenhouse gases while also combating some of these negative impacts of climate change is regenerative agrivoltaics. Next slide, please. So many of our speakers have already given really great overviews of agrivoltaics and looking at the benefits in certain case studies. But in case you aren't familiar, regenerative agriculture is the use of certain agricultural practices, such as reduced or no-till, cover cropping, agroforestry, livestock integration, with the proposed outcomes of increasing soil organic carbon, increasing biodiversity, but mainly to help improve soil health and productivity. Next slide, please. So combining regenerative agriculture with agrivoltaics could offer potential co-benefits of implementation that could help to combat climate change through both, decreasing greenhouse gases, but also offering things like Richard said, climate resiliency and other farmer and ecological benefits that other folks have given in their presentation. So I'll go into each of these categories in the next few slides. But for each co-benefit, I will give a case study for regenerative agriculture and for agrivoltaics. But I just really wanted to note that it's really important that these benefits may vary based on agricultural system, climate, soil type, or solar design. It also may take years of implementation for some of these benefits to show. Next slide, please. Okay, so the first benefit of implementation for both agrivoltaics and regenerative agriculture is, of course, greenhouse gas mitigation. On the left is a study looking at total greenhouse gas emissions of 2 agrivoltaic systems. They're shown right there inside the red square. You can see that both agrivoltaic designs emit less greenhouse gases than the majority of the other energy sources like coal, natural gas, biogas, but a little bit more than onshore wind. And then on the right, we have a study looking at the potential carbon sequestration for various parts of Africa, looking through implementing conservation tillage. This study here estimates 143 teragrams of carbon could be sequestered per year in Africa. So that is a very, very high number. And because of that, I just wanted to highlight that there are studies out there that kind of roll that number back a little bit. There's global meta-analyses that show that no-till may not have as high of a sequestration rate as some studies show if you look at the full deep soil profile. So just a consideration when you're looking at these numbers. There's also saturation rates. So soils cannot sequester the same rate of carbon indefinitely. Next slide, please. And I know I only have 10 minutes, so I'll have to run through these slides quickly, but happy to answer any follow-up questions at the end or when we have the larger Q&A. So for water conservation, we've talked about this a lot today. Agrivoltaics has shown to slow down evapotranspiration rates, soil moisture retention rates can increase, which can lead to lower irrigation requirements. And similarly, regenerative agricultural practices such as cover crops here on the right can increase soil water content. For this study, it was a 7-year study, and there was an 11% increase in water retention and a 22% increase in plant available water through the use of cover crops and maize production. Next slide, please. So for soil health, for agrivoltaics, I put down both positive and negative potential because it's very much dependent on the construction practice of the solar array, which Kai already highlighted. For example, if the soil is graded and compacted before installing solar panels, that will obviously highly impact soil health for a long period of time. However, if you use low impact construction methods, and then in this case study here on the left, add in things like sheep for grazing, you can potentially increase soil carbon, soil nitrogen rates over time. And then for regenerative agriculture, this study shows an increase in topsoil particulate organic matter from the introduction of winter cover crop at a farm in South Africa. And this was true for multiple types of cover crops. I believe they used both vetch and oats in this study. Next slide. Agrivoltaics can also potentially slow down soil erosion at solar sites through adding vegetation. The study on my left is by my colleague, and it was looking at bare soil at solar sites compared to an agrivoltaic site, because bare soil is potentially what solar sites may use instead of vegetating it. And he saw differences in mean grain size and sorting, which is the distribution of grain size, and determined that the bare soil at the first solar site accelerated erosion, while the agrivoltaic site was able to slow it down. And similarly for regenerative agriculture, this study looked at total soil and soil organic carbon losses through conventional tillage when compared to no-till systems. And they found that the no-till plot reduced soil losses by 68% and soil organic carbon losses by 52%. So pretty large decrease. Next slide, please. Then we have biodiversity conservation. Our team at NREL has been working with Argonne National Lab, which is another one of the Department of Energy's research labs, to look at biodiversity impacts of agrivoltaic systems that have pollinator habitat. And over the 4 years of the study, both the abundance and diversity of pollinators significantly increased at agrivoltaic sites. So it can be a really great hub for diversity of pollinators and other types of insects. And for regenerative agriculture, in this study, the use of regenerative practices, they were looking at 16 different orchards, showed an increase in invertebrate biomass and diversity when compared to conventional agricultural systems. Next slide, please. So as Richard already hinted to, agrivoltaics can lead to climate resiliency potentially through the lowered consumption of water and potential yield increases. That can allow farmers to still continue to grow crops, especially during times of decreased water access. And similarly for regenerative agriculture, this is one of the longest studies going on, and it's a 40-year study of corn production. So it was looking at the addition of cover crops and manure application, and they found both increased in yields in full till and reduced till systems in times of drought. Next slide, please. So while the ecological benefits are important, obviously it's very important to pay attention to the impact on the farmer. So for the agrivoltaic study on the left, this study was looking at 3 different cases for a 0.15 hectare farm in Niger. One was a rain-fed system that offered very minimal profits. It was kind of just producing for the family and the community. And the second was the diesel-powered irrigation system, which actually showed negative profit potential. And then the agrivoltaic system that included solar-powered irrigation offered a much higher potential for profit for the farmer. And then similarly, if you look at the regenerative agriculture study, it looked at both conventional and regenerative corn production and found that even if the yields were to be increased in the regenerative agriculture system, because there was reduced input costs and higher crop value of the regenerative agriculture, the farmer was able to have a much higher profitability when compared to conventional farms. Next slide. And we already talked about this a little bit with agrivoltaics. So for crop yield, I had both positive and negative for agrivoltaics and regenerative agriculture. On the left for agrivoltaics, you can see quite a variance in yield for different crops and agrivoltaic systems, which was similar to Richard's results. Unfortunately, we didn't have that 3,000 increase like Greg had, but I have seen both in the sites that I've worked on that most of them in hot climates perform much better, but there are shade intolerant crops like listed here, cucumbers, that don't do as well in certain agrivoltaic systems. In terms of regenerative agriculture, the study was looking at a meta-analysis of the impacts of no-till on crop yield. Here the results showed a decrease in yield for many climates if the crops were irrigated. However, when the system was rain-fed, many of the crops showed increased yield for no-till. Many other practices such as cover cropping and agroforestry have also shown varying impacts on crop yield. So it's always really important to have local research projects to show how these different practices, both in agrivoltaics and regenerative agriculture, can impact crops. Next slide, please. And then I just wanted to highlight some of the potential co-benefits and trade-offs. Regenerative agrivoltaics shows potential to improve farmer health, which Richard talked about a little bit. Offering that shade, lower temperatures really makes an impact At the farm that I worked at, the agrivoltaic farm, the farmer that took over said she would not continue farming outside of agrivoltaics just because she needs that access to shade throughout the day as temperatures get warmer and warmer. With regenerative agriculture, you also see a decrease in use of agricultural chemicals, which can be beneficial to farmer health as well. Both systems have also offered many educational opportunities, as Greg has highlighted, looking in different areas such as energy production, soil health, sustainable crop production, and it can be for a range of different groups of students, all the way down from ages 5 to PhD students we've seen be interested in these types of systems. And then also, like crop yield, there's other areas where researchers have found varying impacts of agrivoltaics and regenerative agriculture, looking at certain outcomes like weed and pest pressure, as well as total soil carbon sequestration potential. The literature out there is very varied, and we don't have an actual number of like, if you had this specific plot of regenerative agriculture using these specific practices, you will sequester this exact amount per year indefinitely. So just something to think about, that some of these numbers are a little uncertain. And in that line, there also may be some trade-offs or barriers to implementing regenerative agriculture and agrivoltaics. We already discussed high initial investment costs, increased labor requirements potentially, and there's always going to be that high learning curve for folks to have to learn new technologies and practices. Next slide, please. Great. So hope that helped give a bit of an overview of potential benefits and trade-offs. I know it was pretty quick, only at 10 minutes, but happy to answer any questions. And thank you all for listening.
Thank you so much, Brittany. Greg, I saw your hand quickly pop up. Did you have a question come up there?
No, I'll save it for later.
Okay, perfect. Are there any other quick questions for Brittany? Otherwise, we can move on and come back at the end of the session. Don't see any hands, so I think with that, we can move on to our final speaker for the day, which is Talita. Over to you.
Yeah, can you hear me?
Yes.
Okay, thank you. Is it possible for me to share my own slides?
Yes, please go ahead and share from your side.
Okay. Okay, is that working for you?
Yes, it is. It looks a bit zoomed in on our side.
Maybe after you make it full screen for viewing, it'll work.
Is that any better?
Yes, that's a bit better. Can you try going presenter mode?
Oh, it is in presenter mode for me. Okay. Is it working now?
No, it's not in presenter mode on our side.
Okay, I'm not quite sure why it's not working, but we might best stick with just you sharing the slides then.
Sure, no problem.
Okay, so thank you for sticking around to see this talk. So I'm Talitha. I am a PhD student at the University of Arizona, but I'm going to be talking through some of the research. I started as a research assistant at the University of Sheffield, looking at identifying suitable locations for agrivoltaics when thinking about two different scenarios. Next slide. So we've heard a lot already about the benefits agrivoltaics could offer, particularly in East Africa, which is the region that I'm studying here. But what we don't know is where agrivoltaics could be most suitable. And so the aim of this study is to answer that question, but from two different but both crucial perspectives. So the first one is thinking about yield optimization. So we ask, where could agrivoltaics produce the highest combined yield of crop and solar electricity? And then the second is thinking about climate resilience, which we've heard a bit about so far. So we're thinking about where could agrivoltaics have the most beneficial impact on areas that are vulnerable to climate change? And particularly with this climate resilience scenario, we're thinking about regions that are teetering on the edge of not having enough water for agriculture, with these areas being particularly vulnerable to even some minor climate shifts that might be expected in the near future. Next slide, please. So to answer these two questions, we use a method called suitability analysis, also known as multi-criteria decision analysis or site selection. Essentially, this method is just creating a map that shows you where the best locations for a specific thing you're interested in might be. So in this case, we're thinking about agrivoltaics. This type of analysis, you combine different spatial data sets that impact the suitability of a location for that thing you're interested in. So each of those input data sets impacts the final suitability map, but some of the data sets impact that more, and that's controlled by a weight that you give to each layer. So this is a method that has been used quite a lot for solar and wind farm siting, largely because it's quite cheap and quite fast, and therefore it can be really helpful in assessing a large area to support the appropriate implementation of something, in this case, agrivoltaics. Next slide, please. And so to do this analysis, we follow 5 key steps. Next slide. So we held a workshop with experts in agrivoltaics, in solar energy, and in agriculture from the East Africa region. And we asked those experts to identify the factors, particularly thinking about biophysical factors, that would influence a location's suitability for agrivoltaics. Next slide, please. So then based on the expert input from this workshop, we collected data that related to those key variables. So you can see the list of the final variables we were able to use on the slide now. So including things like solar radiation, we used GHI to represent that, slope, rainfall, soil quality. Next slide, please. Thank you. So following collecting all of the data, we then went back to our experts and we asked them to compare these input variables to determine how important each one was in influencing suitability. So for example, here we are asking whether evapotranspiration or slope is more important and by how much more that factor might be more important. And these expert comparisons formed the weights that we apply to the input variables that determine the level of impact they have on the final suitability map. Next slide. Following this, we then prepared our data. Next slide. And so because our input data sets that we collected came in different spatial resolutions, some were really fine resolution, some were a lot coarser, and they all use different units. In order for us to be able to compare these and combine them, we needed to reclassify them. So this is just a diagram showing you that process essentially. And And then following that reclassification, we created a specific rule for each input variable that determines how they would impact the suitability. And these rules were different for the two scenarios that we were looking at. So we had a set of rules for our maximum yield and a set of rules for our climate resilience. Yeah, you can move on to the next slide. And the next one. So finally, we combined the reclassified data sets using the weights that were determined by our experts. So you can see the weights here alongside the layers that they're associated with. So essentially, those weights are just combined with the numbers in the data sets, and then we use that multiplication to get our output suitability map. So we'll just jump into some of the results. Next slide. So here we're looking at agrivoltaic suitability across the East African region, thinking about maximum yield. So what we can see is that Uganda and Kenya are coming out as highly suitable for agrivoltaics for maximum yield. You can see this either in the map, or you can have a look at the proportional bar charts. So this is the proportional representation of suitability per country. So in particular, we find that thank you. We find that Western Kenya, Northern Uganda, and Western Central Tanzania stand out as three zones of clustered high suitability for these maximum yield agrivoltaic systems. However, what we also find is that all of the countries in our study region do have land identified as either suitability 7 or 8, which are the highest that we had in this analysis. And this suggests that careful site selection for agrivoltaics means that it could be appropriate in each of the countries studied, as long as you were careful with where you were implementing them. And this means that there's a significant potential for high yield agrivoltaic systems across East Africa. However, the distribution and extent of suitability varies considerably. And this means that the sites that you choose to develop for these systems should be carefully selected. Next slide, please. Thank you. So next we look at the results for the climate resilience scenario, or where agrivoltaics might have the most beneficial impact on climate vulnerable agricultural regions. So we can see that the distribution of suitability areas is significantly different in this scenario compared to the maximum yield scenario. Here, for example, we can see Ethiopia, Tanzania, and Kenya showing significant suitability. However, there is a shift in the suitability patterns, and that underscores the importance of considering the goal of an agrivoltaic system. So that is, what is its purpose when you're building it? Is it meant to produce the maximum yield possible to increase the resilience of agriculture to climate change in that region? Or perhaps there's a different goal in mind, but really considering that base goal is particularly important. What we also find is that areas that may be optimal for maximizing yields could still greatly benefit from the climate mitigating effects of agrivoltaics. Interestingly, if you have a look at Somalia, we see that there's a really high coverage of unsuitable land compared to the other countries in the region. But what we also see is that when land is suitable, it tends to be high suitability. And this again highlights that there's a need for targeted and careful implementation of agrivoltaics. We also observed that countries like Ethiopia and Tanzania, which showed moderate suitability in yield maximization scenarios, emerge as highly suitable in this climate resilience scenario. And this could indicate that these areas are on the cusp of significant climate-related challenges, where the water saving and microclimate moderating effects of agrivoltaics that we've heard a bit about this afternoon could be particularly beneficial. And the differences between these two scenarios emphasizes the importance of considering multiple factors when planning agrivoltaic implementations. And while some areas may not be optimal for maximizing combined solar and agricultural yields, they might be critical targets for building climate resilience in vulnerable agricultural systems. So this again comes back to that idea that the core goal of why you're building an agrivoltaic system is really key to where would be a suitable location for that site. Next slide, please. So just very quickly, we find that there is significant potential for agrivoltaics in East Africa, but there's little overlap between maximum yield and climate resilience scenarios. We see that Uganda and Kenya have high suitability for maximum yield, while Ethiopia, Tanzania, and Kenya come out as more suitable for the climate resilience agrivoltaics. However, Ethiopia and Kenya both show high suitability in both scenarios. And again, this just really highlights that a one-size-fits-all approach to agrivoltaic design and implementation in East Africa would be really inappropriate. And it again highlights how important a clear goal for the agrivoltaic system is when considering where might be an appropriate location for it. Next slide. Yep, that's the end. Hopefully there's still time if anyone has any final questions, but thank you very much for listening.
Thank you so much, Talcott. That was a great presentation. I see Paul-san has a question. Do you want to go ahead?
Thank you very much for a very good presentation. I want to know if weather variables are actually important in terms of how effective the system could be, or the suitability of agrivoltaics. So if they are important, my thinking is that in Africa, weather stations are sparingly distributed. So how were you able to get the information in terms of temperatures in different regions? Or if you're using, let's say, geographical information systems, did you do some ground truthing, and how was it easy or was it difficult? Because now you have few weather stations distributed within Africa. Thank you very much.
Yeah. So each of the data sets I used are data sets produced by different organizations. There is definitely fewer data points available in the East Africa region. And so some of those data sets do have a level of interpolation involved in them. So some of it is just based on an equation coming from those few weather stations that you're mentioning. What I will say is that each of the data sets I'm using have all been carefully analyzed by those that produce them in terms of the uncertainties that are involved in them, in terms of the biases that they may carry. And that's something I'm definitely aware of in this work, but the data is what it is, I suppose, in this area of the world, in that if we had more weather stations, we could probably be a bit more certain with it. But I am working with the best data sets I can find. But yes, it's definitely something to keep in mind, that there could be some local variation that isn't captured in this kind of large scale spatial data set. And because of that, I would always suggest that this kind of analysis is great for kind of high level, large scale analysis, but you really do need to go to local sites to carry out further analysis before you implement a site.
Thank you very much.
Thank you so much, for that question. Yeah, we have 1 more minute if there's any overarching questions for any of our speakers. I think today's session has been really, really great, and we've had some really great insights into both the business case side and the benefits, as well as some of the considerations that need to go into place when planning for some of these systems. So I think this has been really great discussion. And I appreciate everyone for staying on a bit late. Paul, please go ahead. You have 2 minutes.
Yes, and thank you very much. Yes, this I echo what you are just saying. This is a great presentation, and thank you for all the presenter and the organizers. So the question I have is generally for, a general question, but just, to ask if there are any highlight for best practice, because of course we talk about the benefit of agrivoltaic, but I believe it is also important to maybe design best practice meaning, the maintenance, so, cleaning the PV panels for soiling, and so on. So that's the one. The second one is, for example, and just like what the last presenter has been talking about, it is of course important to really understand the goal when the agrivoltaic plant is, is set up, because I believe depending on whether we want to take advantage of the power of the photovoltaics panel, and depending on the location, especially the study that was done with Arizona, different location, it is important also to take into account the aspect of the panels, the solar panel by themselves, not just the crops, but also because depending on the location, the quality of the panel may matter, but also what is called temperature coefficient, which is the decrease of the efficiency of the panel as a function of temperature. And if one wants to produce power, of course, that's going to be impactful. And I believe it will be important to include this in the, for example, any economic studies, to take into account all those aspects. Those were the 2 points I wanted to mention.
Thanks for that really important point, Paul. Yeah, Kai, I'm not sure. Do you want to share anything about any sort of guidance to best practice that might be available? Is there somewhere potentially where there's opportunities to produce more sort of knowledge products, or is there something you can point us to?
Yeah, great questions. And largely, a lot of the existing resources that are out there are really focused on, a US-centric perspective or a European-centric perspective. And while many of those resources are applicable to agrivoltaics in general, there are going to be, so many variables that change depending on the region you're working in, the grid infrastructure, or especially if you're in a very rural community, and also depending on the community needs. So much of those resources do give great basic guidance, but specific projects will have very different needs.
Great. Thank you so much for that, Kai. I think this has really been something very interesting. I think I see lots of opportunities. There's been lots of great questions in the chat, and I see we have even had a request about getting technical support for Nigeria to support their NDC 2.0. So I think this is really the kind of area that gets us very excited. So I want to thank you as well as all of the speakers today for sharing such great insights, and thank everyone for participating in this webinar. I would just like to ask everyone if you would take 2 minutes to quickly fill out the survey, which has shown up on your screens now. This is really helpful for our perspectives. And yeah, if you have any further questions, queries, or interests in this regard, please feel free to reach out to both the AfCAP Secretariat as well as some of the colleagues from NREL who have, and some of the other speakers as well, who've added email addresses and contact details in the chat. But besides that, thank you so much, everyone, for this great session, and look forward to carrying on this discussion. Thank you so much.
Thank you, Roy. Thank you, everyone.